טוב. עכשיו, אז אני לא זוכר איפה עצרנו בפעם הקודמת. אתם רוצים להזכיר לי?
היה לנו מזמן.
זהו, אתם לא זוכרים כלום.
הצגת לנו את הבלוק, equations ואת ה-density.
כן, זה אני זוכר, ואמרתי שנדבר על רמזי, לדעתי, אבל לא ממש דיברנו עליו.
עשינו אבל בשיעורי בית.
מה?
עשינו בשיעורי בית.
זה האפקט ההומוגני.
מה זה?
האפקט ההומוגני. זה ה-inhomogeneous.
כן, על זה דיברנו.
וגם צחקנו על סטארק, האשמנו אותו. במה שמגיע.
זה לא מצחיק בכלל.
לא. אוטלר טאונס שיפט.
אטלר טאונס לא יכול להיות שדיברנו. דיברנו על... לא, אטלר טאונס זה משהו אחר.
משהו אחר.
על סטארק שיפט מאז, AC סטארק שיפט, מאז נוהגים לקרוא לו הלייט שיפט. אני חושב שהאמת זה שם יותר ראוי. אבל על ה-DC סטארק שיפט, אז עוד לא קיבל שם שונה. טוב, אז התוכנית להיום, לסיים, כעיקרון אני רוצה לסיים עם 2 level, אבל נדבר על רמזי fringes. First of all, I think it is recorded by definition, and the other thing is that it has to be in English, even though nobody here needs to requires that, because it is recorded and we have English speaking, and I think that it is set to be recorded, and it will just appear automatically as. So we're going to talk about Ramsey fringes, and I'll try to tell you why, because today it seems like a bizarre thing why to go for, but it's still something that is useful to know. And then we'll talk about photon echo. Those are all kinds of coherent effects in a 2-level system that are very useful. In this case, photon echo is a way to eliminate inhomogeneous broadening. To be exact, static inhomogeneous broadening. And then, I guess most of our meeting today will talk about 3-level. Oh wait, before the 3-level there was one more thing. The steady state of a single driven atom. And then most of what we will do, we'll talk about the 3-level systems. Next week we'll talk about 4-level and then 5 and then 6. No? We'll stop at 3. Why? Because we're physicists. We're lazy. And here we'll see beautiful, interesting effects. Things like primarily the existence of dark states. And what results from them. That is the effects like, we'll talk about stirrup and about outlier towns splitting. That will appear also. And EIT, electromagnetically induced transparency. Those sound like nice acronyms to understand. So we'll try to cover a few of those. Next week, that's it. I mean, enough with quantum matter, classical light. We'll start talking about classical light only. You see, primarily we'll talk about coherence. It is good to understand classical coherence before we discuss quantum one. And then after doing that, understanding of quantum coherence will make a lot of sense. So, we start with Mr. Ramsey. As I told you, Mr. Ramsey received a Nobel Prize for understanding something or suggesting something that was that seems today kind of, well, what? But let's first say that okay, so we're going to talk about okay, so if we have a two-level system, then we're talking about clocks, okay? We're talking about atomic clocks. And in an atomic clock, there, that's it. Let's say something about what. So first of all, what is a clock?
Something that measures time.
Okay. And then, by the way, it goes there. First of all, that's a problematic definition, because do you know what the definition of time is?
Something that a clock measures.
Yeah. What time is what a clock measures. And by the way, what is distance? What is the definition, the physical definition of distance?
Product of time and velocity.
Well, that's honestly today, yes, that's the definition, because the speed of light is constant of nature. So we don't really need to define distance independently. But the old definition of distance was what a meter measures. That actually is.
Bat, right?
What?
Wooden bat. It says 1 meter.
Well, I don't think it ever was made of wood, but there was a time where there was this meter in Paris that defined the meter. And of course, what is mass? What a kilo measures. And then you need to find what a kilo is, what a meter is, and what the clock is. Now, so, and if we think about a clock is an oscillator. Doesn't have to be that kind of oscillator, and a counter. 1, 2. Now that means that if you want to read a good clock, then you need a good oscillator. You need the ability to count. Now, what makes a good oscillator? Good oscillator is an oscillator that is well, first of all, stable, doesn't change its frequency. Repeatable and uniform. What do I mean? So first of all, like stable, it has a narrow, very well-defined frequency, or sorry, let's call it actually sharp. So if a clock, so first of all, just a clock, that's an oscillator plus a counter. Now, during time, the oscillators changed. The standard oscillators have changed, and we have improved them over time. And recently, also the counters changed a lot. But that is not what bothered Mr. Ramsey. And then we were talking about an oscillator, and a good oscillator needs to be sharp, meaning its response in frequency. If you try to drive it at different frequencies, it must respond at a very specific frequency with a very small. So you want this. You want it basically infinite. The response in frequency should be very sharp, should be stable. Stable, generally stable over, I don't know, locations, temperature, conditions. It shouldn't suffer from, and the main thing, it should be uniform. So for example, for that reason, I don't know, pendulum is not that great. Why? Its frequency is low, so that's not very convenient. It's not very stable. It depends on its frequency may change if you move it around to other places on Earth. And third, it's not very uniform. Why? Because it's very hard to make two pendulums that are exactly the same. They never are.
So uniformly you can make two different oscillators, but it will be
Yes, I want to make them as much as possible.
same.
Yeah. Like this is a short-term. Let's. Those two are properties of a single oscillator. Those are properties of many. This is a property that says in short time it doesn't change the frequency. Frequency is stable over short times. What does this say? It is stable over long times. That even if I don't know, it will oscillate here. I'll take it to Norway and bring it back. It doesn't change, and this means that the different oscillators are the same. Now we can make many efforts in making oscillators, like man-made oscillators. They can be sharp with a very good and well-defined resonance, and they can be stable, maybe because you stabilize them. I don't know, you stabilize their temperature, you stabilize their environment, or maybe you make them extremely robust. There are many things that engineers know how to do. But there's one thing that they cannot really do. There's no way around that. We have limited precision, and man-made oscillators will never be perfectly uniform. So what we did in the past was to say, yes, all quartz oscillators or diamond oscillators are basically equivalent, but we will take one and we'll call it master and say all the others should be aligned according to it. Well, that's okay, but then you have a problem. What happens if something happens to the master? Or if, there's nothing that makes it unique except for the fact that you named it so. So here comes the point that, okay, we want a reference, an absolute reference. So for this, we need an absolute frequency reference that will allow us to first and that's so and that's where the atoms come in. That's where atomic transitions play a role. That's what the atom. So when we say an atomic clock, it's not an atomic bomb. And even when we say an atomic nuclear clock, it only means that the transition that we're talking about is a nuclear transition in the nucleus. But and there is work going towards that direction. But so the way an atomic clock works is that first you have a good oscillator. And you use that good oscillator to derive the frequency that you think will excite the atoms, because it hits the atomic transition. In this case, we're talking about radio RF atomic clocks, meaning that we're looking for an atomic transition in the radio frequency. So a good oscillator that generates, say, 9.1 gigahertz, approximately. Then what do? Well, you shine it on, so you want to check. So you shine it onto cesium atoms. It should be a little bit more, there's a little bit more of a protocol to it. We'll talk about the transition that this excites in a moment, but you shine it onto cesium atoms. It's actually a gas. Now, cesium is a metal that in room temperature is just it's a metallic solid, but when you put it in vacuum, there will be vapor, cesium vapor around. There's a vapor pressure. If you heat it up, you have more. Don't hold cesium in your hand, not in air. It's kind of explosive. And then what? And then just like detect. Like I want to check if absorption. And then what will I do? I'll use that to correct the oscillator. So this oscillator should be as good as possible, and it is, but it also some slightly tunable. And you use the atoms, they don't make good oscillators usually. Quartz oscillators usually have a much better finesse, much stronger signal than like if you would use the cesium atoms themselves to generate the clock frequency, that is very hard to do. So when we say an atomic clock, we don't mean that the atoms are oscillating. We only mean that we use the atoms. We have a small like cuvette with atoms where we check constantly that our frequency did not move. And we believe that all atoms are the same, and therefore if anybody else does the same, we will get the exact same frequency. And we can also check it. We can make two independent cesium atoms, and then we can compare their two oscillations, which should have very, very little relative drift. And the relative stability is what defines the quality of the clock. Now we want to, so we said something about other things. Now we want to talk about probing the atoms. Now, the atoms are, so first of all, in cesium atoms, there are this 9.1 gigahertz. What is it? In the ground state of cesium, cesium is a hydrogen-like atom, has one electron, one valent electron. So its states are very similar to those of the hydrogen, but those of you who suffered studying for Moed Bet in Quantum 2 must remember probably the hyperfine splitting. So, and that is because the electronic spin of the electron in the ground state interacts with the nuclear spin of the cesium nucleus, and this generates a splitting between the two spin states that normally would be degenerate. And this splitting between the F equals 4 and F equals 5, as far as I recall, levels of Y4 and 5, because that's what makes the total spins, and then M equals 0, Ym equals 0, Mf. So why go for Mf equals 0? So that it will be magnetic insensitive, that magnetic field, stray magnetic field will not affect it. So because the Mf equals, and this transition is 9.1 gigahertz. So what do we do in order to probe the cesium atoms? First, now those two states are normally thermally populated. And because 9.1 gigahertz is extremely small, it's very easily excited thermally, you can assume that initially a cesium atom is 50-50, very close to 50-50 between those two states. If you shine directly on it, this 9.1 gigahertz, you'll see nothing. So the first thing that you need to do is empty at least one of the levels. How? Well, you drive, you shine light that is resonant with F equals 5 to some transition above, optical transition. That's called pumping. But it's not resonant with F equals 4. Why? Because of this 9.1 gigahertz separation. That's enough so that you selectively excite one of them, and if you continue to shine that light, then whatever electrons that were here, well, they go up and then they spontaneously fall down. If they fall down here, then you pump them again, and if they fall down here, then they're stuck. So you pump this one empty. You don't have to be perfectly exact to do that, and then you try to run a pulse that will. Then you check your oscillator, your 9.1 oscillator. How do you do that? Well, you shine 9.1 gigahertz radiation onto the atoms, and you want to see them transit. Okay. So now let's understand what you, and then now you want to be very, very selective. You want to make sure that only if you're exactly at the right frequency, which is not exactly 9.1, there's some several more digits afterwards. That when you're exactly at the right frequency, the atoms only then will go up. Now, and here, Fourier is important. You want, and it has to do, basically you would like to make, so what do you want to make sure? You want to make sure that you're driving the atoms from ground to excited exactly on resonance. Now let's remember what happens on the Bloch sphere when we excite exactly on resonance and when we excite off resonance. Now, the point is that the strength, the detuning from resonance is our, which component of the Bloch vector? Sorry, of the driving field. Okay, a driving field on resonance is exactly in the x direction. The detuning makes this. So now and then now what we would like to do, we want to make sure that we take the atoms from down and put them up there. How do we measure if we put them there? Well, we do the same trick again of checking if there's population here. Just like we empty it, we can check if there's population here. We shine light that is resonant with this state and not with this state, and then see if we have fluorescence. Because if the state was empty, then there will be none. And if the state is repopulated by the 9.1 gigahertz, then we will see fluorescence. So there's this optical shelving level. Now, all those details, I must say, it's nice to understand. So if we have here population, we pump it up and then let it fluoresce, and we either use that fluorescence to pump out the population or to measure the existence of the population. So now let's remember. Okay, so if I can take the population up, now it is clear that from uncertainty, that it's probably better to do it over a long time. Why? Because longer time means better precision for frequency. Like the uncertainty delta omega delta t is greater larger than 1. But in the Bloch picture, it's even easier to understand this. And that is, okay, if I do it, like I give a short pi pulse. Its area is pi, its duration is short, so the field is large. The field is the x component of the field vector. The detuning is the x component. So that means that if I have a short pi pulse, then it's there's mostly a field. Maybe there's a detuning, but it doesn't affect much. And the mutation around this, on resonance or slightly detuned, doesn't make much of a difference. You end up upstairs anyway. But if you make the field smaller, then the detuning makes a small detuning makes a much bigger change of direction. And then the slow mutation, because this field is slower. The fact that the mutation is slow or fast doesn't matter. The fact that the direction of the field, the of course, this is the Bloch field. It's not the real field, but in the Bloch space, the field in the Bloch space is now has a very strong angle like that, and the atoms will not end up upstairs. So we would like to make, so we want here a long interaction, and it is clear why we would like it to be, and the thinking was that means a long pi pulse. Make it as long as possible. How long can you make it? As long as the atoms remember. So the longest you can make it has to do with the both the decoherence and the lifetime. Well, we'll come back to that later. The transition lifetime. It's usually T1. It can be also, well, T2 is also important because you want to excite, if you have an ensemble of atoms, so you want to excite all of them, and you want to make, actually it's the T1 or T2, it's the minimum of the two. Oh, and because usually it is limited by T2, because T2 is usually shorter than T1.
What does T allows?
What?
T allows? The first one for lifetime?
T1? What?
Transition.
Transition. That's short for transition. But the problem is, so if you have, and today we do, the ability to just hold the atoms still, cool them down so they don't move very much, hold them in a trap so they don't move at all, and then shine on them for as long as you want, and then you'll be able to do that, and assuming that you made the gas dilute and you're holding them still, and you will be limited eventually by the spontaneous lifetime of the excited transition, which can be, in this case, extremely long. I mean, this, conceptually at least, this target state never decays. So if you don't, it becomes not a question of lifetime, but more a question of being able to keep. How long are you willing to wait until you ask the atoms where they are? And how long can you keep your oscillator sufficiently stable before you ask for a correction? So that's, but in the 60s, when atomic clock started, they couldn't do that. Why? Because they didn't have ways to cool the atoms and definitely not to trap them. So they were working with an atomic oven in vacuum. They put there a piece of cesium, heat it up. What happens? they have a vapor, a hot vapor of cesium atoms running in that oven. They make a hole in the oven. So there's an atomic oven with a hole. So atoms are spewing out of here at thermal velocity. So then you can try to say, okay, they're spewing in all directions, but then we can put another, and then we'll have a beam, an atomic beam running in vacuum. Now, those atoms are running at about, I don't know, about 500 meters per second. They're flying through. And that means that when you interact with them, okay, so, and then the question was, and then they had like a tube. This thing was running in a tube. This whole thing is sitting inside vacuum, but that doesn't matter. And eventually those atoms hit a wall and stopped. So now the problem is that if you want to make a long interaction with the atoms, you run into a problem. Well, what do you do? So you make an antenna. So you have like a horn antenna. Really, it really actually looks like a horn. That takes where, I don't know, that oscillator that we had before is shining RF onto the flying atoms. And then on the other side there was, and then here at the end of the tube there was a detection light. So this was detection light and a detector. The problem is that now the duration of the interaction with the atoms is just limited by their flight time. How long does it take for them to fly through your antenna? You can make an antenna of, I don't know, 10 centimeters, 20 centimeters. And then you can calibrate from that how long you can interact with the atoms. And then you have another problem, and that is that the velocities are not exactly equal. There's a velocity spread here. And because there's a velocity spread, that means that you don't excite all atoms the same. They have a Doppler shift, a different Doppler shift. They also have a different interaction time because they're flying through. So you cannot make that large. If you try to make it large, you run into inhomogeneous problems. So that means that in atomic clocks at the time were limited primarily by this, by the flight time of flight. So like here, tau equals just time of flight through the field region. And you couldn't make that field region very large. You can make the tube as long as you want, but you cannot interact over a long distance. And then came Ramsey and said, okay, so yeah, but I can divide my pi pulse. And he could even think of saying, well, the pi pulse doesn't have to be long. You know what? Let's make it short, really short, as short as possible, almost a delta function. How can that be good? The point is, let's divide it into two halves with some time in between. So what happens? Okay, the first half, it's extremely short, everything happens very fast, the detuning is irrelevant if there is one, and the atoms very quickly rise here, all atoms. No selectivity, on resonance, off resonance, doesn't matter, all of them are here. Now, the point is that now, so all that Ramsey understood was we can have, instead of one antenna, we can have two, with some separation in between. You know what? Okay, I'll keep it there. So there is our tube, and here is our detection light. Here's our detector that we use to feed back onto the oscillator. But then he said, okay, the antenna is not really that large. We have just, so what he does is he splits the field. It's really like that, splits the field to a small antenna here. And we have a small region, field region. All atoms fly, and then it splits, and then here another small antenna. And then here, nothing. And then what happens when the atoms fly through nothing? And the answer is they still feel something, and that is the detuning. The field within that, so here all atoms went up. And now we have, but now here they are precessing around the detuning. What does it mean? It means that the atoms acquire a phase at the atomic rate, and the field acquires a phase at the field frequency rate. And if those two are not the same, then they will acquire a phase difference. A phase difference on the Bloch sphere means that you move. So all atoms were initially here, but if there is a detuning during that time, you can say that they're nutating around the detuning, or you can say that they're acquiring a phase, a relative phase, so they're moving around. And then we come with another short pi pulse. So now we can see that it becomes a question. So here, this is short pi over 2 pulse. What does it do? Okay, let's talk about the one stages. Ramsey experiment. So one, it's a short pi over 2 pulse. What does it do? It takes all atoms from ground to here, because they're nutating very quickly around the field. And during the delay, not the same tau, I don't know, tau. During the delay, the atoms are nutating around the detuning, so you acquire a phase That's the relative phase between the atom and the field, which is the detuning time tau d. Delta omega, okay? Omega atom minus omega laser. And then, so that means you acquire a phase which in the Bloch language takes you around, well, you know, I don't know, takes you around somewhere. If you're exactly on resonance, nothing happens, you're not moving. But if you're off resonance, then you will end up somewhere, I don't know, somewhere around the equator line. And then you try to have another short pi pulse. Pi over 2 pulse. And I think that you calculated and you saw what happens in this case. Well, let's see, but it's very clear to think about that. Okay, if you're on resonance, perfect. Up, stay, don't do anything, another up, everybody's up. But of course there are other, if you're slightly off depends on how much. The question is, how much is that phase? Okay, if that phase is, I don't know, exactly, say, I went up here, now I drifted because there's some detuning, say I drifted up to here, and then I had another pi over 2 pulse. What happens? Stay. Nothing. Stay here. So I have half the population, not as much. If I have more, if that phase is actually pi, then this is catastrophe. We go up, phase takes us here, and then the pi over 2, instead of taking us up, take us down back. So nothing happens. But of course, as that this phase can add up, so this phase could be 2 pi, and then we'll end up again. So what will we see? We will see as a function, so if I just look at a single pulse, if I just have a short pi pulse, then I'll ask, how does the population respond? We'll discuss this. So I plot this is omega atom, this is omega laser, and now the frequency of the laser, and this is I don't know, excited population. So because the pulse is short, if this is a short pi pulse, we'll excite most of the population, even if we're on resonance or off resonance, because the detuning is not very important. So we will have something that looks like, and it usually depends on the pulse, it looks like a broad, it can be a sink, it can be a Gaussian, it can be anything depending on the, if the pulse itself is a square pulse, then it will be a sink. So this is tau and this will have a width of the order delta omega laser of the order of 2 pi divided by tau pulse.
This is for the pi pulse.
Right. For any pulse, actually. Okay, so now, but on the total Rabi case, on the total Ramsey case, okay, and that's for a Rabi pulse, and if it's a Rabi pulse, all you can do is try to make that smaller by making the tau pump longer. So if you want a narrow response, the only thing you can do is make it a long interaction. But in the Rabi case, or in the Ramsey case, then what we actually have is this. A very short response we'll immediately discuss what is the, that would be delta omega. And then we'll come back. Very similar to a double slit experiment. And we can see, we just mentioned that. If you are exactly on resonance, you're perfect. If you have a detuning that gives you a pi pulse during the dead time, during the delay, so this is actually not 2 pi, it's just pi over the tau delay. So that's a big difference. And that means the fact that Ramsey understood that when you don't interact with the atoms, you can still use that, because the atoms are still flying and they have a coherent memory and they remember what you did to them. So you can interact with that memory later. That was an important understanding. And until today, sometimes, hot atom clocks still use that method in some way, in many cases. And the main thing is that, and if you look at this and you see the single slit and double slit experiment, it's because it's exactly the same. This is a double slit experiment in time or frequency instead of in space. Tov. That was a little bit about Ramsey. So now let's say something about, okay. Now what would limit, so and here what do we want to do? Well, of course we want this fringe to be as narrow as possible. How narrow can it be? Well, first it depends on how long the atoms can remember. Because they need to, if this distance is too long such that the atoms forget, then nothing will happen. How long can they remember? Well, if it's a single atom, or if this is a very, very well-defined cluster of atoms where all of them are flying at exactly the same velocity and with no, some stray fields or any other problems, then this will be the lifetime of the excited state. But in a real experiment, in a real ensemble of atoms, it will be shorter. Why? Because not all atoms are the same. So that's why how narrow this can be is limited by the coherence time of the atoms, and we would like to make that as long as possible. And then the question is, okay, how? What can we do? Now there are things that we cannot do anything about. Everything that is homogeneous, that happens to all atoms, is something that there's very little things that we can do about. But there are things that we can actually do. At least think about, well, come on, it's annoying. Every atom remembers. Okay? What did I tell you? Look, if you have a Doppler shift, you have a Doppler broadening, and what happens? Well, some atoms are at zero detuning, they don't move. Some atoms are a little bit fast, so they're blue detuned, so they're moving one way. The others are moving in the other way. And if I look at the entire ensemble, then I'll see nothing. It seems like I have decoherence, everything is lost. But that's not true. Each atom still remembers. The problem is that every atom remembers its own state, but they're not all the same. So I would like to make a trick to somehow eliminate this effect. So you can think of it in the so what can we do? And then so now we can talk about photon. So now I want to talk about photon echo, and that's a nice trick. Say that I want to do so the question is, I told you, look, in here we do nothing. So now I actually want to do something in between. And what I want to do in between is to add exactly in the middle. So this is pi over 2, this is pi over 2, and this would be a pi pulse. What does that help? So,
This is the new subject, right?
Right. So we're talking about photon echo. So now I'll try to, let's,
And these fringes are the Ramsey fringes.
yeah, these are the Ramsey fringes, and you understood why they're good. They're good because they allow you to measure a much narrower transition, and then, assuming that you know how to identify the middle fringe from the rest, then you can make sure that you have the accurate frequency much better. By the way, what do you think? How can one identify whether they sit on the right fringe at exactly the atomic frequency and not one that is shifted by 2 pi over the delay? Suggestion? Yeah?
Try the left and the right. Check.
What?
Check the left one and right.
Well, okay, so let's talk. Well, it depends. I mean, they could be. Maybe there's a difference between them, but maybe they're exactly equal. So that's. How do you know? I can check the one to the left and the one to the right. You're telling me, look, if I'm here, then this one will be higher and this one will be smaller, right? So you say, no, that's not good. I want to go to the one where to the left and to the right they're the same. True. That can be done, but you can do that only if the fringes are the way they are here, not too dense. If you can, if you can make the pulses, if you can make an ideal Ramsey experiment, then you will give very short bursts where this is extremely broad, and then the difference between these will not be enough to be detected. But it has to do what?
Change the time of propagation.
Yes. You can start with a short relative delay, which means that you can start with no relative delay at all. Just give one pulse. What will you see? You'll see this. Okay, so now you know approximately where the center is. You're not accurate. And then what? Start increasing the delay slowly. And then make sure that you stay on the center. You constantly stay on the center. So that will, because this fringe is the only one that doesn't move. The others, the more delay you get, then all the others are moving. But this one is the only one that doesn't move. So the way they tune that is by identifying the. And so now we're talking about the photon echo. So we understood that a Ramsey experiment, and basically any experiment, is limited by and for precise measurement. Now, so we want to kill T2 star and make it only T2, meaning kill inhomogeneity. But okay, so one way to kill inhomogeneity is to actually kill it. So if you want no Doppler shift, make sure that all your atoms are moving at the same velocity and that it is always the same. No, you're leaving me? He's angry. Apparently the angry birds are... What? Okay. So now this is so here comes a clever trick. Okay, so let's see. If I give okay, so we let all atoms jump very quickly here. Now we leave them. So they start dephasing. Those that are on resonance stay there. The others, some of them are drifting here, the others are drifting there. Very quickly we'll lose it. Now we can let it go, but let's take for a moment the point that we actually did that. And then what? Let's hit them with another pi pulse. Okay? Now I hit them, they started moving there somewhere. I'll hit them with another pi pulse. Okay, if they're here, it doesn't do anything. I mean, no, if they're here, they're flipped, whoop, to the other side. If they're exactly here, they'll end up here. If they're here, they'll end up here. If they're here, they'll end up here. So, let's see, we have the same situation, we flipped the situation, but now, those that were running forward, previously, let's call this one forward. So these are running forward, these one are running backwards. Now what happened? Okay, everything flipped onto the other side, but now those that are running forward are behind. And those that are running backwards are up front. So you flipped their order, and now after a while, they'll both end up together again.
The same while.
There will be an echo. And this echo means that, well, you know, this one was running slowly like that. You flipped it here, it continues running like that and ends up with everyone. Okay, and then the other one was running this way. Okay, you flipped it here, it is still running the same way. And after, so if exactly in the middle, so if we talk about the photon echo, we have a series of pulses that look like pi over 2 tau delay pi and then you can try so I don't know, tau, let's call this one tau 1 and this is called tau 2. You put another pi pulse, pi over 2 pulse. You're doing a Ramsey experiment with a flip in between. Now, why, and if those two times, so when tau 1 equals tau 2, you will see a revival. Revival of coherence. Why? Because, so what did we assume here? We assumed that, okay, during the time between the first pulse and the pi pulse, the flipping pulse, the atoms were running at some rate away from each other. And then what did we assume? That, okay, we flipped everything to the other side. I'll flip as well. And then at the same, if they are running, still running at the same speed and at the same direction, they'll meet each other again, and then we will have an echo time. That will be the time to hit with another pi over 2 pulse. So if I say keep that one fixed and scan this time, I'll see that most of the times I see nothing, and then when these two times are equal, I'll see a revival. What is that good for? This means that we can annihilate, we can eliminate the inhomogeneous incoherence. Let's be clear though, we can eliminate the static inhomogeneity, meaning that we assume that they're running at the same pace, that they didn't change. If the atoms that were running here away, when they flip to the other side, are running at a different rate, then they won't. This so a single pi pulse can and then we will, so what do we see? So okay, so I'll so if we have so if this is, say, T2 or tau 2, and this is where we have tau 1, and this is the excited populations. We'll see that when the pi over 2 pulse comes exactly here, we'll see a revival. And then what? So this is where tau 2 equals tau 1. And if I change tau 1, so now I make the first delay longer, you're making, somebody went and then somebody else came and then, so, and then we'll see that this excited population if I change tau 1 to I don't know, like, and we will see a decay, so this will decay at the time scale that is not T2 star, but it's actually the homogeneous T2. So that will be longer. And that's why it's called a photon echo effect. Now, what can we do if when I try to I want to make this delay longer and longer, right? Because we want to make the Ramsey experiment builds on long delays. We want long delays. So that's something that is good. It eliminates the inhomogeneous, static inhomogeneous. Static inhomogeneity can be eliminated by a single pi pulse. But not all inhomogeneities are completely static. For example, if you have an inhomogeneous magnetic field, well, it changes also in time. So maybe now and later, not exactly the same. I don't know, so other things can be also time varying. And then the question, so what can we do? So if I want a long delay, meaning that I want to let the different atoms, they can run crazy as far as they want. They can make many pies around the circle, and then we flip them around, run the same many pies in the backwards direction, and then everybody will realign and come up. That won't happen. So what can we do? Suggestion.
Why won't it happen? Because the magnetic field.
Because what happened during tau 1 is not exactly the same as what happens during tau 2. They're the same duration but not the same time. So the field here, the magnetic field or whatever it was, would not be exactly the same as it would be here. So well, we can make more pi pulses. If a trick worked once, let's do it again. Meaning, okay, suppose that I give here a pi pulse, so it flips this one to here. Move everybody backwards. Now we let them run. Okay, run for a while. And then I don't want to hit my pi over 2 pulse again yet. But I don't want them to, but I want to, I want to erase again. How? Flip the other side again. Okay? Like I had a tau, first tau 1 was short. So not a lot happened. Then we flipped. We erased that one. Assuming that was short. So things didn't change much. Now what? Okay, I don't want to measure yet. I want to continue delaying. But I cannot rely on the fact that everything will be the same. So what do? Reverse again. Okay, give it another pi pulse. Hit it on the other. And then what? This will reverse. This will erase whatever was happening previously that is not the same as. So you don't have to put just pi. You can make, I don't know, divide this time, not to 2 durations, but I don't know, 10. And then what? Pi over 2, tau, pi pulse, tau, pi pulse, tau, pi pulse, tau, pi pulse. Hit them. And then every time you erase again, what will you be left with? You assume that from 1 pi pulse to the next, which is now a shorter time, nothing happened. So you're static around every pi pulse, but you're not necessarily static from 1 pi pulse to the next one. So you can yes. Okay. So, and finally there's the last trick, and that is the photon locking. Photon locking is a nice thing, and that is, okay, if I give a pi over 2 pulse, they're here. Now, if I continue the pulse, they'll just continue. But what happens if I flip the phase of the laser? So the laser was a cosine omega laser T. Okay? Now, and then I flip it from cosine omega laser T to sine omega laser T. I give it a pi over 2 phase. What does that do in the block? If you remember, the x and y axis of the block sphere are the real and imaginary part of the atomic coherence. Relative to what? To the laser. So if I flipped the laser from being real to imaginary, then this is just like as if saying, okay, maybe I can say, look, the laser is now here instead of here. Or you could say, no, the atoms are now here. And then what happens when we now continue shining light? Nothing. So that's why this is called photon locking. If you just, okay, you give a pi over 2 pulse, then flip the phase of the light and just keep it on shining. And what happens? They are locked here. They don't move. So, and then, so well, there are all kinds of tricks that you can play with that. They will basically hold, and this really eliminates everything except for T1, population loss. Because this doesn't matter what happens to them as long as they're, unless they got a kick and just fly out to unknown where, they'll stay there. So if you just say, okay, now let's measure, okay, let's do that, lock them there, and now just measure how long you have population excited like that, then you will be able to measure basically the same thing. The tau, the homogeneous tau, T2 that exists. Tov. I enjoy talking about this subject, as you can see. So even when I'm tired, I talk a lot. I think that maybe, do you want to take a break? Okay.
If you want.
For some reason. So let's have a 10-minute break. And that basically almost finishes what I had to say about the 2-level atom, and then we'll talk a little bit about the 3-level atom and the interesting things that can happen over there. And they are interesting.
זה לא בסוף זמן החיים, נכון?
מה זה?
זה לא בסוף זמן החיים, עדיין טיפה למטה נתיים.
כן?
מה מודדים פה מבחינת זמנים, נגיד?
מה? כאילו, מה שמודדים בסופו של דבר זה כמה population יש לנו ב-excited state.
ואיך אני מתרגם את זה לזמן?
אתה יודע שאם אתה בתדר הנכון, אתה מצליח להעביר את ה-population ל-excited state. אם אתה בתדר הלא נכון, and you want to make that distinction as precise as possible, that the smallest mistake in frequency will make a large difference in population. So that's actually what the Ramsey fringes manage to manage, because it allows you to, even though you're working with short pulses that are basically broadband in frequency, you can still have a very precise measurement by just using the delay between the pulses as a coherent memory that tells you whether you're on resonance or not.
So the measurement of the excited population gives like a feedback loop which tells me if I'm
Yes.
at the right frequency.
Right.
And the frequency is the base for the time.
Right. So basically the time is the oscillator. So, okay. All that we're talking about now is about the how to design a really good oscillator. So, okay, so first make the best effort to make an oscillator that doesn't move. And then to cancel the slow possible drift that it has, or to cancel the uniformity, or ununiformity of the different possible oscillators by locking them to an absolute reference. So that's what the atoms give us. They give us an absolute reference that we want to lock onto as precise as possible. Okay. So one last thing, and that is, if you have a single driven atom, then you have only one time scale, a single driven atom that really doesn't move. So no inhomogeneous effects. It sits in one location. So all there's not really a decoherence. This T2, where does it come from? For example, it comes from collisions with other atoms. There's no other atoms to collide with. So if you have a single steady state of a single driven atom, So still, for a single atom, we have the same Bloch equations. We have this U dot V dot W dot equals, and what is that? So just to remind you, this is like yeah. What did I do here? These are things that I wrote too long ago. Oh, okay. So this is delta times V minus, we'll see in a moment, minus U divided by, I don't know, basically T1, but there's 2. In a moment I'll explain why that. So those are the Bloch equation, and that is delta times U. Delta is the tuning, and we're writing the precession equations with the decoherence put by hand. So that is so what do we assume here? There's only one time scale for decoherence. What does decoherence do? It kills, it acts like an exponential thing that gives an exponential decay for V, for U, and for W. Assuming they don't change, then only these things will just cause them to decay. The rest is the standard nutation equations. And the only thing that I did here was to assume that everything decays on the same time scale. You can tell me, wait, but here you made it like half. The point is that indeed the population, honestly I don't remember why that half is, but I know that it's there. So you ask Emmanuel and he will tell you. And then you tell everybody else. And then tell me, so I'll remember from this thing. Okay, and the point is that we can actually say, okay, so let's say that I want to measure the steady state. If I want to measure the steady state, then I'll say this equals 0, this equals 0, this equals 0. And those are just algebraic equations that we can solve. So we have 3 equations for U, V, and W. There's a detuning, there's the field strength, and there is so yeah, just do this, and then we can have a solution. So it is And then the reason that I'm showing you this is because this is a common way to explain, and that is the W of steady state. I'm writing ST instead of SS. So, and we can write it like that. I'll immediately say what S is. S is the saturation parameter. Well, the steady state for you is the detuning divided by omega naught times S divided by S plus 1. And V steady state equals the detuning. So I'll call 1 over T1, I'll call it gamma. So that's the rate. So, and this one goes like gamma over 2 omega naught times the same parameter S divided by S plus 1. And what is S? So this is one thing, and S is so, and this is the decay rate, and this is the saturation parameter. Why saturation parameter? So you can see that as the driving field becomes stronger than what? Than the detuning and the decay rate, then what will happen? This factor will approach okay. It will approach 1. But I think that there was a mistake. This is this minus 1, sorry. Forgot about that. Important. Indeed, so when you have a very strong field, this S is large. If S is large, then the steady state W approaches 0, which is exactly what you expect. You expect to have like an equal, like you hit the center. But you can see, okay, this we knew, we know. But we find that when we drive the atoms at steady state, they will have some steady state coherence. And they also depend on the same parameter. And they also have values, but their behavior is different. So it's like, and now we can, we can ask ourselves, how does So, the other thing that I wanted to say is that we can look at this is the real part of the atomic coherence. I think it was like a real part of it was like C1, C2 star. If you remember, those were the and this one is the imaginary part, or C ground, C excited. And they're defined real and imaginary relative to the field. Now, okay, so you can see that we can explore this in all kinds of limits, and they're all very interesting. The main thing is, if I want to look at these two, the real and imaginary part, then we will see that the real part, let's explore it as a function of the tuning. Okay? So let's explore, we can explore W as a function of, if this is the omega atom and this is omega. So I want to look at this as a function of omega atom. Okay. You know what? I'll draw it like that. So I'm looking at W as a function of the detuning divided by gamma. Why? Because they have the same units. I want to be unitless. So what is this? Well, for a given, this looks like a Lorentzian. Okay, as a function of a detuning. So that will be a Lorentzian. With a width well, we can actually, we need to be a little bit more careful. It will be a Lorentzian, but we need to write it over there, and then the width, because this is S divided by S plus 1, the width of the Lorentzian obviously will depend on the strength of the field. You can make the calculation for that. Because I didn't want to take a look at these two, but when I look at also, now let's draw also here, this will be U and V. So if I want to look at U, U has the detuning here. So as a function of the detuning, it becomes a detuning times a Lorentzian. So U will look like this. When we change the detuning divided by gamma. Whereas V, it only has gamma here, but it doesn't have that. So this will be U. And if I want to look at V, it would look more like this. That means that is actually important. Where is it important? When we try to trap atoms. Now, these are things that if you go to Lev's course, he will teach you more about. But if you constantly shine light on an atom, it will reach this steady state. And then the question is, what happens when you are, and how do we use light to trap atoms? So there are, first, how do we use light to cool atoms? For that, we use the Doppler shift. What does it mean? If I have atoms sitting here, then I would, I'm sorry, if I have the atom sitting here, and so I can shine light of them that is slightly red detuned relative to the atomic transition. So it is. So then that means that atoms that are standing, not moving, they will be off resonance and they will not be very much affected by this light. But atoms that are traveling towards me will see a blue shift, and they will absorb the light. Okay, if they absorb it, then they become excited. Then they emit it. They emit in all directions. So they will have a recoil of how much? Of approximately absorbing one photon. And a photon has momentum. It does deliver momentum h bar k. So every such absorption event dissipates 1 h bar k of momentum, and therefore the atoms that are moving towards the beam are slowing down more than the atoms that are standing or maybe moving in the other directions. They're less affected. So what do? You shine light from here, and 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 you shine. You have 6 beams, and then you're stopping the atoms in every direction. So that slows them, but that doesn't stop them. I mean, that doesn't trap them. They're not held. So, and then you can add another trapping beam. Now you want that to be a trapping beam. You don't want it to, you just want it to hold the atom. So it needs to be actually off resonance. If it's on resonant, then the atoms will absorb the light and very quickly they'll be gone. So you want it to be very off resonant. What do you want actually? So you want to be in a regime where there is you don't actually excite population, so you want W to be small, far away from resonance. And far away from resonance, this is what delivers the trapping force. The residual U is what gives you the trapping force. What do I mean? Well, if you remember, we talked about the light shift, which previously was named by the name that should not be named. Then now the light shift, if you go back, is directly related to that. Now the light shift that's what it is. It's actually an energy shift of the atom. That means that when the atom sits where there's strong, detuned, but strong light, there's a shift of its energy. Where? Slightly towards the red. That means that atoms are actually attracted towards the location where there's strong light. Why? Because the energy levels there are lower. By moving there, they feel like it's a potential. If the energy changes, it looks like as a function of location. Then it's then it's a potential well that they can sit in. So if you have a red detuned trap, meaning a very strong beam that is red detuned, the light shift generates a potential that has a well where the light intensity is high. So just by doing that, focus the light into the vacuum, which is highly detuned, and the atoms will be trapped there. Why? You can say because they feel the potential, or you can talk about this U, which is the gradient of the force. That's, and I'm too tired and there's too much I want to cover today than to actually explain this in detail. So, but you can also do that in the other direction, meaning you can also use a blue detuned beam. If you have a blue detuned beam, then you see U flips a sign. If U flips a sign, it's actually repelling. I mean, in that case, atoms are repelled from high intensity. But that means that you can still make a trap by making a dark location that is surrounded by light. If you can do that, so if you can have some trick to make a blue trap, then the atoms will be held in the dark, and whenever they hit the wall, the light wall, they'll be reflected. Why? Because when they hit the light, they experience a light shift that shifts their energy up or down, and they need to get that energy from somewhere. Where do they get it? From their kinetic energy. The kinetic energy stops, and then they are being reflected back. So, yeah, and this saturation parameter is important and very useful. Well, and that's it. Okay. So let's talk a little bit about 3 levels. We have something like half an hour. So we want to talk about 3-level systems. We'll say something about stirrup and others. So, okay, when we have 3 levels, I don't know, like 1, 2, 3. This is called a lambda system. And usually in this case, we have 3 levels, and usually we have only 2 lasers. So like, and there could be a detuning. I don't know, like delta 1, and this is like E1, and this one could have a delta 2, a detuning, and this would be E2. Now, so here, now this is a lambda system, but of course you could have a situation that actually looks like that, like 1, 2, and 3. This is a V system. You could also have a ladder system, like 1, 2, 3. As I'll show you in a moment, they can all be treated under the same. So this can be, I don't know, like a V. So this is a lambda system, this is a V system, this is a ladder. Now, whenever I draw this, I mean, there are lasers. Why only 2 lasers and not 3? Because usually, for example, we can talk about the situation when those 2 are ground states, different ground states of an atom, and this is one excited state. And the laser, so those 2 are close in energy, say something like several gigahertz away from each other, and this state, this excited state, is reachable by a laser light, which is, I don't know, 100 terahertz away. So this is like very far away from those 2, and there's no, and because those 2 states are very close, well, if I'll shine an RF light, an RF field, I'll be able to couple them directly, but I don't. Or maybe there's no dipole moment connecting them. Because what is important is that when we talk about the Hamiltonian, we can remember that the Hamiltonian is, first of all, H0. In a moment we will remind ourselves what H0 is. That is, I don't know, there's a ground state. So let's say 0, and then H bar omega atom 1, or so let's give things I'll give this a name. What did I call it at the time? Okay, you know what? Let's keep it like 0 is the energy of 1, and this is the energy of 2, and this is the energy of 3. Whatever that is, but everything else is 0. That's the Hamiltonian. And then what? There's the, I don't know, like 1, 3, the way that I wrote it here, times E 1, and also D 2, 3 times E2. Now, those are, or initially they're time dependent. So this is actually, so I can say that, you know, this is whatever H0 is, and then, but I should be careful and just write this D is like an operator. Okay, so, but let me tell you so yeah, and this is, those are operators. That means that what this field is, so this by definition is Hamiltonian, it looks like something like this. There's here or I don't know, h bar omega. I don't want to use omega. I call them epsilon, so let them still be epsilon. And then here, this laser can couple states 1 and 3. So let me flip. I'll call this one 2 and this one 3. Why? Because I want it to be like that. Here I'll have D12 times E1, and here I'll have D12 times E1. Now those are still a function of time, and here I'll have D12 times E2, and D12 times E2, and then here there will be 0. Why? Because there's no coupling between state 1 and state 3, those two states directly.
Shouldn't some of the D's be 3, 2?
Of course. These guys. Now, better not fall. And now, so, and here I assume basically that the state is what? Is C1 times 1 plus C2 times 2 plus C3 times 3. So that's our state. And this one is time dependent. They're all dependent on time. And this psi is dependent on time as well. Now, again, we remember that E1 of t is basically some E1 field times cosinus omega 1 t, and that E2 and now we can do the following. So again we can move to the rotating frame. Where is that rotating frame? Now let's see. I want to say, I call state 1 as being energy 0. So this state, in my view, doesn't move. It doesn't acquire any phase. This one acquires a phase according to epsilon 2 divided by h bar times time. But I don't want that. So I will rotate it at the laser frequency. Which laser? The laser that couples here. So instead of doing that, I will write the same psi as being, well, B1 times 1 plus B2 times what? Times e to the I minus maybe omega 1 t. True? Yes, I think omega 1 is the one that goes up. And plus B3 times e to the... Now let's see. This one has an energy which is going, well, in this lambda system, which is the one that I want to now solve, this one is the one that goes like what? Okay, it has basically E3, but E3 is related to what? To omega 1 minus omega 2. Okay? So in this case, I will write here minus I omega 1 minus omega 2. And those would be now, and these, so I'm rotating at the laser frequencies, and I'm assuming the lasers are close to the transitions. So this is approximately, this is not far from epsilon 2, and this is not far from, this is not far from epsilon 3, and this is not far from epsilon 2 divided by h bar, of course. And then, what else? Now, of course, if I did it here, then it would be different. If I say that this one doesn't move, then this one would get omega 1 and this one would get omega 2. And in this case, then this one would get omega 1 and this one would get omega 1 plus omega 2. So the concept is the same, it's just the rotating frame needs to be chosen according to the scheme that we have. And now we can just again write, so what we do is the same as we did always, like I h bar psi dot equals, well, what? H psi, and we can do this. And then because of that, those psi dot, and we will end up, we will throw again the counter-rotating terms just as we did before. Which are the counter-rotating terms? So whenever we have h bar omega 1 minus epsilon 2, this is a small term. But if we have h bar omega 1 plus epsilon 2, throw it away. The same goes for this one, so h bar epsilon 3 and h bar, so we're going to do the same trick, and then we will have this. So Now the rotating wave approximation brings us to the Hamiltonian at the rotating wave. The rotating wave approximation Hamiltonian looks like this. 0. Let's put h bar outside, okay? Okay, 0 remains 0. And then instead of here epsilon 2, I'll have delta. The detuning of laser 1 from the atomic frequency. And what will I have here? I'll have here delta 1 minus delta 2. The detuning difference. And then what will I have here? I'll have here omega 1. And here, omega 1 star. And what will I have here? I'll have here omega 2. And omega 2 star. And here 0. The transition, if you remember, basically this is what the two-level system is. So what we're doing is actually two-level twice. There's these two levels coupled by this laser, and there's these two levels coupled by this laser. Well, actually here, now just why did I say, yeah, and why is it delta 1 minus delta 2? Yeah, well, I think that, yeah, I think that's, it needs to be delta 1 minus delta 2 just to make sure that I didn't make a mistake. Yeah, well, there's omega 1 minus omega 2, so it must be. Okay, so now, and now again, we can look at this. Now, okay, this is a 3 by 3 Hamiltonian. Not very hard to, so okay, now the question is, do we have a Bloch sphere picture of this? Unfortunately, no. Too many things. This lives in a larger dimension space. Maybe you could think of like one laser rotating one, and the other one is connected to it like a double pendulum or things like this. It's very, I don't know of a convenient way, but what we can do is now we can treat this and basically treat it in the dressed picture. Meaning, this is the Hamiltonian. The bare Hamiltonian is with these off-diagonal terms disappearing. And that bare Hamiltonian, well, of course, we have 3 eigenstates with 3 eigenenergies. But when the field is on, we can now diagonalize and find the dressed states. So, so let's look at the dressed states. So yeah, and I'm studying this. That was 1, 2, and 3. This is the system that we're studying. So we can look at the rest states and energies of this. So I want to diagonalize this matrix. A 3 by 3 matrix is not very hard to diagonalize, and I want to diagonalize it on a special case, and that is the case of what we would call two-photon resonance. Meaning that this detuning, there can be a detuning here, it can be even large, but the two detunings are the same, so that omega laser 1 minus omega laser 2 equals also in spite of the detuning here, it equals perfectly this energy separation. So let's do that. Diagonalize H rotating wave approximation at delta 1 equals delta 2 equals delta. So the Hamiltonian that we have is basically this: 0, delta 0, omega 1 star, omega 2 star. And this is what we want to diagonalize. Okay, so let's do that. We will have so okay, so what is the equation that we need to solve? So I'll have here, so I'll write this H minus lambda like that equals this of minus lambda, and we can write that as being minus lambda times minus lambda squared times delta minus lambda plus lambda times omega 2 squared minus what? Omega 1 absolute value squared plus what?
Times lambda.
What?
The minus omega 1 should be with
yeah,
a plus
times
sign
lambda.
and with a lambda.
Right? Is that true?
But with a plus sign.
Plus, indeed. And give me the last one so that I won't make a mistake.
0.
Right. Okay. So let's just have here plus lambda times omega 1 absolute value squared. Good. And that equals 0. And then so we can immediately see that we have one solution with lambda equals 0. And there will be, so that's one solution, and we can throw that one out. That is one solution. And we then can find two more solutions. There will be lambda plus minus. And I can tell you, I think I can tell you what they are. Yeah, they're equal. So we see that there are new energies, and those will be like plus minus half square root omega 1 absolute value squared plus omega 2 absolute value squared. So we have three eigenstates, three eigenenergies, and they have three eigenvectors. There's an eigenvector that goes, now this eigenstate with a 0 energy is interesting because it's 0. We have a rest state with an energy 0 that is not affected by the field. It's always 0. These have energies that actually make sense because when you have a field, you'll have a light shift, things move, things change. So those are, those are, here you change the field, their energy changes. But this state is somehow not affected by the field. So this is the dark state. And we'll see why we call it a dark state in a moment. Let's see what are the states that are related to this. There are, together with this, you have the state V0, and then there are the states V plus, V minus. So let me tell you what V0 is. You don't need to believe me. So, like
101. It would be like
yeah,
both the grounds.
it will be right. The state that is related to V0 is a combination of only 1 and 3, but doesn't contain state 2. So I'll write it for you. It is actually this. This is just a normalization, 1 over square root of omega 1 squared absolute value plus absolute value omega 2 squared times what? Times omega 1 star omega 2 0. And these guys, they look like 1 over the same. But here, they have omega 2, omega 1, and then here they have 1, plus or minus 1. It doesn't really matter. They look something like that. I am primarily interested in this guy. As I told you, it has a unique property, has the energy equals 0, and it doesn't involve the excited state. So now let me show you some magic. Okay? If this is my system, I want to transfer population from 1 to 3. Can I do that without ever being in 2? It seems, I don't know, if you look at the scheme, it seems like bullshit. How could that happen? How can if I want to transfer population, if all population was here, I want to end up with all population here, well, the reasonable thing to say is to say, okay, turn on laser 1, put population up here, and then turn laser 2 and put population there. But I want to tell you, okay, maybe there's another solution. I'll do something else. I'll first turn on laser 2 and then slowly let it down and then turn on laser 1. Okay, I turn on laser 2. What happens? Nothing. There's no population here. But let's look at this state. This state, when laser 2 is on, and laser 1 is off, this state is actually, I made a mistake. This is 2, this is 1. My apology. True. It has to be. I'll explain why. Why do we call it the dark state? Which will be the state in that situation? Laser 2 is very strong. Which state is not affected by the light? This guy. So if you only have laser 2 on and laser 1 off, then the state number 1 is the dark state. Why? The light doesn't talk to it. So it's not affected. In the end, I'll end up with laser 1 being very strong and laser 2 being small, as practically 0. Then what will be the dark state? Oh, Number 3. This is the dark state. But the point is that there's a dark state also in between, right? In between, the dark state is a combination, a coherent combination of laser 1 and 3 that remains like unaffected by the light, even though both lasers are there. Why? Because they destructively interfere. You know, population, here you don't have population, you have an amplitude. And this amplitude, if there is a coherent superposition of state 1 and 3, it can be with such a phase that whatever is excited from here interferes destructively with whatever is excited from here, and therefore nothing is excited. So, and that's what the dark state says. You have a coherent superposition of amplitudes of 1 and 3 that is arranged in both phase and amplitude exactly such that their contribution going up destructively interfere and die. So now let's assume that I start with the situation that 1 is the dark state, and I end in the situation where 3 is the dark state, and I slowly change. I just do an adiabatic change. So what has happened? Okay, I start, population was at 1, and 1 was the dark state. So population is at the dark state. And then what happens? I slowly change the intensities. What happens to that? The dark state slowly changes. But this is an adiabatic change. So where is the population? In the dark state. And then what? But the dark state is slowly changing from 1 to 3. And eventually, in the end, I end up with this laser being strong. This one is 0. And what happened to the population? All of it is here. Where was it on the way? It never was here. And so, first of all, the order of the light was counterintuitive. I started by turning on laser 2. Then there was a time where the 2 overlapped. And eventually, I ended up with only 1. So it's like oh, okay. We need to finish, and we will just now, because we actually understood the major important thing. So I can think of, this is time. I turn on omega 1 and then omega 2. This is intuitive order. And then you will pass the laser population to state 2 and then to state 3. What will you suffer? Spontaneous emission. During the time, you need to do this really fast because this state decays. Population decays. I don't know where. It can decay out, it can decay in, but it decays. It doesn't, you want to do a coherent transfer, the population doesn't stay here. But then I can do the counter intuitive. And that is to say, look, no. Start with omega 2 and then turn on omega 1. And surprisingly, in this case, and this will couple to the dark state. And if you do this slowly, then you will transfer population from state 1 to state 3 without ever being in state 2. So how can that be? So if I look now at what happens to the population, then I will see that what happens to the population is that population of state 1, if this is the population of state 1 starts high, and then here falls, and eventually becomes 0. The population, this is of state, I don't know, this is B1 absolute value square. And the population of state 3 starts 0, builds up, ending up like that. And if you check during the situation how much population was in state 2, the answer is nearly nothing. Now the question, why nearly and not exactly nothing? Exactly nothing is in the adiabatic limit, but nothing is completely adiabatic. If you could do this truly adiabatically, so if this transition can be really slow, then nothing, truly nothing will be there. Now let me lift the magic a little bit. The existence of dark states is a very important and useful trick in quantum optics everywhere. So to know their existence is very useful. Now let me lift the magic just a little bit. Meaning, let's think that I'm doing this with short pulses. Instead of continuously changing, let's think that what I'm doing is I'm making a pulse of omega 1, omega 2, omega 1, omega 2, omega 1, omega 2. Okay? Now let's think what happens here. I shine omega 1. So I'll drive, it's a short pulse, quick, and it doesn't do a lot. So it will take some population here. It will. And then will come this. The question is, can this one come and take everything down? The answer is yes, it can if it's strong enough. If it's a pi pulse, right? So like, if I want to drive some population here, I start with I need a very weak pulse to drive population up, because there's a lot of population here in the beginning. So I don't want to drive everything. If I'll give a pi pulse, everything will be up. I'm not doing that. I'm giving a small pulse. So a small fraction of that large population is going up. And then when I want to dump everything down to 3, what do I need to do? Boom, hit it with a pi pulse. Large. Then what? After a while, then I'll keep on, and then I'll shine this one again. It will need to be a little bit stronger because there's less population here in order to excite population up. And this one will need to be a little bit lower in intensity in order to drive this population down, but not excite whatever you had there already back up. So the population does go through number 2, but doesn't stay there. It just flip. Whatever goes up immediately goes down. So, and that's a nice and clever trick. And this is called stirrup. Stimulated, rapid, adiabatic passage. So it's adiabatic, it needs to be slow, but it's rapid. So that, and there are many other implications for the dark state, but those we will discuss briefly in the beginning of the next, our next meeting, and then we'll start discussing light coherence, and we'll start discussing the light, the classical properties of light, and the quantum ones. We're getting close to quantizing the field, but this will not be next week, probably the week after that. And we have 2 more months, and there's a long time. יאללה, ביי, סליחה שהארכתי.
תודה. אבי, לאן נעלם האיבר של הדלטה?
איזה מהם?
בערכים העצמיים.
האמת היא שהוא לא מופיע. כאשר אתה על... אוקיי, האמת היא לא, טוב ששאלת, צריך לעשות את זה קצת יותר לאט. המצבים האלו משתנים, דלטה מופיע, אבל אתה צודק, הכתיבה הזאת היא בהנחה שגם דלטה הגדול הוא 0. זה הסטייטס כאשר דלטה הוא 0, אבל גם כאשר דלטה איננו 0, זה מה לא משתנה בו. כלומר, דלטה יופיע פה בנרמול, האומגות האלו ישתנו קצת בגלל שדלטה יהיה, אבל האפס הזה תמיד נשאר. אז התכונה שכאשר אתה מתחיל מאומגה 1, כלומר אתה מתחיל מאומגה 2 חזק ואחר כך מסיים באומגה 1 חזק, זה עדיין עובד. סטיראפ עובד on resonance, on perfect resonance, וגם off resonance as long as you have all that it requires is 2 photon resonance, not also single photon resonance.